Welcome to Organic Chemistry. Today we are going to explore a fundamental and exciting concept called syn and anti-addition. We will learn exactly how the direction from which new atoms attach to a molecule completely changes its final three-dimensional shape, and why this specific shape is absolutely critical in the real world. To start, let us imagine a flat piece of bread. If you want to add butter and jam, you have two choices. You can spread both on the exact same top surface, or you can put butter on top and jam on the bottom. In organic chemistry, molecules with double or triple bonds act a lot like that flat piece of bread. When we add new atoms to them, the direction matters immensely. Building on our bread analogy, let us define the chemical terms. An addition reaction happens when new atoms attach to the carbons of a multiple bond. If both new atoms attach to the exact same face of the molecule, we call it syn addition, because syn means together. Conversely, if they attach from opposite faces, one from the top and one from the bottom, we call it anti-addition. This simple directional difference completely dictates the molecule's final shape. Now that we understand what these additions are, let us look at how we control them. Think of a crowded dance floor where people are moving too fast to pair up. If you provide a sticky mat where they must stop, pairing up becomes easy. In chemistry, a solid metal catalyst acts as the sticky mat for gas or liquid molecules. Because the metal is solid and the reactants are gases or liquids, we call this heterogeneous catalysis. This sticky mat leads us to a crucial physical limitation. When hydrogen gas lands on the solid metal, it breaks into individual atoms that stick flat against the surface. When the alkene molecule comes down to react, it lands on that same flat surface. Because the metal acts like a solid wall, it completely blocks the bottom of the alkene. This physical restriction is what we call a surface geometry constraint. Let us visualize this constraint clearly on the screen. In this diagram, you can see the flat, solid metal catalyst sitting at the bottom. The two blue hydrogen atoms are stuck firmly to its surface. As the alkene molecule approaches from above, it can only interact with the hydrogens from the side that is touching the metal. The metal physically shields the entire other side, ensuring that both hydrogen atoms attach to the exact same face of the alkene. While a flat surface forces syn addition, what causes anti-addition? Imagine trying to walk through a front door, but someone very large is blocking it, forcing you to use the back door. When a molecule like bromine adds to an alkene, the first bromine atom forms a bulky triangle-shaped structure on top of the bond. This massive triangle blocks the entire top face, forcing the second atom to attack from the completely open bottom face. Before we move on, let us see this with a concrete example of syn addition. Here is the chemical formula for our starting materials. We are reacting 2-butene, which contains a carbon-carbon triple bond with one molecule of hydrogen gas. Conceptually, we are going to use a solid metal catalyst to break that triple bond and add the hydrogen atoms. If we increase the amount of hydrogen, we could potentially break the double bond too. But here, we are just adding one equivalent. Let us solve this reaction step by step. We are given 2-butene and hydrogen gas, and we need to determine the three-dimensional shape of the final molecule. We choose a solid palladium catalyst to facilitate this. As we learned, the palladium acts as a sticky mat. The hydrogen gas breaks apart, and the individual hydrogen atoms stick flat against the metal surface, waiting for the alkyne to approach. Continuing with our reaction, the alkyne molecule lands on the palladium surface. Because of the surface geometry constraints, both hydrogen atoms must attach to the exact same face of the triple bond. This yields our final product, 2-butene. Physically, this means the two bulky methyl groups are pushed to the same side of the new double bond, creating a very specific three-dimensional geometry. Now that we have seen the final answer, let us formally prove why this specific geometry occurs. The mathematical and physical reasoning relies on the solid metal surface. Because the metal acts as an impenetrable wall, it completely blocks the bottom face of the alkyne. The hydrogen atoms have no choice but to add from the top face simultaneously. This proves that heterogeneous catalysis with surface constraints will always guarantee syn addition, giving us the cis geometry. This brings us to our second scenario, anti-addition. Here is the formula for our next reaction. We are reacting cyclopentene, which is a flat 5-carbon ring with a double bond, with liquid bromine. Notice that we are not using a solid metal catalyst here. The reaction relies entirely on the electron-rich double bond attacking the bromine molecule. Let us see how the absence of a flat surface changes the outcome. Let us walk through this mechanism. We start with cyclopentene and bromine. The double bond attacks the bromine molecule. The first bromine atom attaches to the top of the flat ring. This forms a bulky, positively charged triangle called a bromonium ion. At the same time, the second bromine atom is kicked away as a negatively charged bromide ion, which now floats nearby, waiting to finish the reaction. Continuing the reaction, that negatively charged bromide ion must now attack the ring. However, the bulky bromonium ion triangle is completely blocking the top face. Just like a blocked front door, the bromide ion is forced to attack from the completely open bottom face. This results in our final product, where one bromine points up and the other points down. This is a perfect physical example of anti-addition. Let us formalize the reasoning behind this result. The proof lies in steric hindrance, which is a fancy way of saying atoms take up space. The first bromine atom forms a massive triangle that physically occupies the entire top face of the molecule. Because two things cannot occupy the same space, the second bromine atom is sterically hindered from entering the top. This proves that the second atom must attack from the opposite face, guaranteeing anti-addition. So, we have proven how these geometries form. But why does this matter in the real world? The three-dimensional shape of a molecule dictates how it interacts with the human body. Many pharmaceutical drugs act like keys that must fit perfectly into specific cellular locks or receptors. If a chemist uses syn addition when they should have used anti-addition, the drug will have the wrong shape. It will not fit the lock, rendering it useless or even dangerous. Let us summarize our key takeaways. We learned that syn addition adds atoms to the exact same face of a molecule, typically forced by the flat surface of a solid catalyst. Anti-addition adds atoms to opposite faces, usually because a bulky first atom blocks one side. Most importantly, we saw that controlling these reaction mechanisms allows chemists to predict and build the exact three-dimensional shapes required for life-saving medicines. You have now mastered the basics of syn and anti-addition.